Alright, as with most things in this book, we have another lengthy question. At the end of these chapters, they put a lot of fun questions to make you think about applications and other cool facts about things. So this one deals with the transformer. And the statement is a transformer takes an input AC voltage of amplitude V1 and delivers an output voltage of amplitude V2, which is determined by the turns ratio V2 over V1 equal N2 V1 over N1. Which we kind of saw last question. If N2 is greater than N1, the output voltage is greater than the input voltage. Why doesn't this violate conservation of energy? Answer: power is produced is the product of voltage and current. If the voltage goes up, the current must go down. The purpose of this problem is to see exactly how this works out in a simplified model. Alright, so part A. In an ideal transformer, the same flux passes through all turns of the primary and of the secondary. Show that in this case, M2 or M squared, the mutual inductance, is equal to the self-inductance 1 times the self-inductance 2, where M is the mutual inductance of the coil and L1 and L2 are their individual self-inductances. Alright? So B. Suppose the primary is driven with an AC voltage Vn is equal to V1 cosine omega t, and the secondary is connected to resistor R. Show that the two currents satisfy the relations L1 di1 dt plus M di2 dt is equal to V1 cosine omega t. L2 is equal to di2 over dt plus M di1 over dt. I don't know why those are S's. And then minus is equal to minus I2R since it's connected to the resistor. Alright, that should be pretty simple. Part C, using the result in A, solve these equations for I1 of t and I2 of t. Assume that I1 has no DC component. And then D, show that the output voltage V out is equal to I2R divided by the input voltage Vn is equal to the turns ratio. And then calculate for part E, calculate the input power Pn is equal to Vin I1 and the output power Vout is equal to Vout I2 and show that their average over the full cycle is equal. Alright, got our hands full with this statement, so let's dive in. Alright, so the solution is suppose that the current I1 flows in coil 1 and I2 in coil 2. If phi is the flux through one turn, then we have phi1 is equal to I1 L1 plus M I2 is equal to N1 phi. Okay, we got to remember that with these things and the inductances, we set up the fact that the current and the inductance led to the flux as well. So now we're just applying it, and since we have two currents or two loops, we have to have the self-inductance and the mutual inductance. So mirroring this, for flux 2, we have I2 L2 plus M I1 is equal to N2 flux. Notice that both of them are related by capital phi, so we'll just go ahead and solve for it. Okay, so what this tells us is that we have I1, L1 over N1 plus I2 M over N1 plus is equal to I2 L2 over N2 plus I1 M over N2. Now, if we were to take turns turning a current on and off, so if we take a turn and we set I1 equal to 0, that would cancel out the I1 terms in this equation, and we would see that I2 times M over N1 is equal to I2 L2 over N2. Similarly, if we did the same thing for turning current 2 off or setting it equal to 0, we would get another cancellation that L1 over N1 is equal to M over N2 respectively. Notice how both of these things are related by N1 and N2. So if we solve for the ratio of N1 and 2, what we see is that we have M over L2, okay, and then N1 over N2 for I2 being 0 is L1 over M. So if we set these two things equal to 0, or set these two things equal to each other and solve, what we see is that we cross multiply, we get M squared is equal to L1 times L2. That's awesome. Alright, now in part B, find the EMF from the flux stated above. Okay, well, for situation 1, we have EMF 1 is negative time derivative of flux 1. So the only thing that changes with time based on the flux 1 is the current. Okay, and we have to set that equal to V1 cosine omega t. And for equation 2, for EMF 2, what we see here is that the only thing that changes is currents, but instead of the voltage, we have to set it equal to negative I2R. Okay, multiply the first equation 1 by L2, and what we see here is that we have we have L1 times L2, and then we have L2 di2. So what we can do now is substitute in the results from part A. So we know that the product of L1 and L2 is m squared, and we know that we found L2 di2 dt in equation 2. So it's just a matter of substituting in what we have. Welcome to circuits, welcome to physics. It does get messy, so be very careful. What this tells us here is actually kind of cool. So with this, if we substitute in everything accordingly, with L1, L2 going to m squared, and then we have the underbrace there, L2 di2 which is equal to minus I2R minus m di1 over dt. What we see is that the di terms cancel because we have m squared on both of them, plus or minus. So what we're left with is negative I2 m r is equal to VI L2 cosine omega t, which is awesome because now we can directly solve for the second current just by dividing the negative MR over. That's awesome. So now let's substitute this current into equation 1 and take the derivative. You see that we get some cancellations of the m, go figure. The derivative gives us omega sine t. And then what we have to do now is shove that over and isolate di dt. So we see here, when we minus that over, we can factor out a V1 from both and an L1 from both, and then divide it by L1, so we're good there. So from here, now we just need to take the time derivative or time integral and isolate I1. So that's where we get a 1 over omega sine omega t from the integral. And then we have L2 over R times cosine omega t, since we already had that as the derivative. Yeah, so it worked out pretty well. Again, it can get messy solving for equations, so just use what you have. Understand that the results might be much closer than you think. All right, so in D, we're concerned with the amplitude of this ratio. So V out over Vn is equal to I2 over R over V1 cosine omega t. Okay, so I2 over R, which we found last time, which from the current 2, which we found last time, we can sub that in. We see that the R's cancel in the numerator. After the substitution, the V1 and the cosine cancel. So we're left with negative L2 over M. But we saw that this again is equal to the ratio of N2 over N1. Let's go back and find out why. In part A, we solved for the ratio of N1 over N2 with respect to M and L2. However, these were flipped around. So we found that N1 over N2 is equal to M over L2, and what we have is L2 over M, so we just need to flip that fraction, and we get N2 over N1, and that's exactly what we're trying to solve. That's awesome. All right, last but not least, part E. The power can be found in the current using PI, or PN is equal to VN I1. Okay, so we know what VN is, and we know what I1 is, and we got a lot of simplifying that can be done. We have a factor of V squared, or V1 in both, so we get V1 squared over L1, and you see we get a cosine, sine, cosine, and cosine squared. Ugh, gross. And then P out is equal to V out I2, which is the easiest one we've seen, except now we have the I2 squared, so be careful, you get the R's cancel from the I squared term, so you get L squared V1 squared over M squared R cosine squared. So after a full cycle, what we see here is that the average of cosine omega t is 1/2. Okay, so 1 plus 1 over or excuse me, yeah, because over a full cycle you get 1 and a 0, and then divided by 2 for the average. That gives you 1/2. But also we see that cosine or sine and cosine at 0, and you get a 0 plus a 0 over 2 is 0, because sine and cosine have opposite values like that. So the average of Pn, we can just plug in a 0 or 1/2 accordingly, is equal to V1 squared L2 over 2 L1R. P out, similarly, cosine squared goes to 1/2. So plug that in. You see in the m squared, we can substitute in what we found earlier, which was L1, L2, and a factor of L2 cancels. And thus what we see is that the average of Pn over a cycle is equal to the average of P out. That's actually a really good thing to see.